Okay, looking at, as you can see, this new chapter is going to be on acids and bases. Now, this makes complete sense, believe it or not, because we just finished a chapter on solutions. Solutions, well, acids and bases are just an example of a different type of solution. All right, specific type. All right, something happens in this solution we're going to learn about. You've heard about acids and bases. We remember pH. It has something to do with pH.
Oh, yeah.
Do you remember what pH? What do you remember about that?
7.
7
norm.
Is your norm. Is
And then everything else that's higher is basic, and everything that's lower is
see, that's great. You remember that. Now, the thing is, you're going to learn today. I'm not today, but this chapter. Why? All right, because that's something. It's a perfect example of something that you guys have learned probably throughout middle school, biology. You just memorized it. And many of you remembered it. You know, like above 7 is basic, below 7 is acidic, and 7 is neutral. But why? Why is that? Nobody has any idea. And you're going to learn has to do with particular kinds of ions that are formed when acids dissolve in water. And you're going to find out which particular ions they are. They're called hydronium ions, and we'll see. But anyway, we're going to start off, first of all, with just how we could tell an acid from a base. And I'm going to do a whole bunch of little demonstrations. Basically, all I'm going to do is test each one of them. I have a whole bunch of stuff up here I'm going to test to see if it's acidic or basic. Now, you guys ever seen this before? These papers, they're red or they're blue. Anybody know what they're called? If I put them in an acid or a base?
Oh, they're the thingies.
They're the thingies, exactly. That's the technical term.
Right?
The technical term. And I can tell if it's acidic or basic by the thingy. Anybody know what the thingy's called?
Strips.
Test strips. Well, that's okay, but that's what are they made of? What's in here?
Iron.
Iron. No. Magic. No.
Magic.
If I put a red one and a blue one into water, they both come out red and blue. They don't change.
Right.
But I'm going to test something that we know is an acid. Let me grab
How do we know that water isn't an acid?
well, we just tested it.
All right.
Okay. Well, something we know is an acid, like, for example, it says it on the bottle, hydrochloric acid. If I test that, let's see what happens. If I put both of them in there, that's okay. I didn't put it down. All right, I put them both in here, and they're both going to come out what? They both come out red. All right, so they started out one red, one blue. They both come out red. All right, that's what acids do. They turn oh, I almost said the word. Litmus. You ever hear of litmus? Litmus paper? And they turn litmus red. Okay, I mean that doesn't make it an acid, but that is something that acids do. They do turn litmus red, and we're gonna put all these over here after I test them. And that's one way we could tell. Now I want to see if there's something in common for each of these. All right, so put that light off for a second. All right, I'm going to test a bunch of stuff, and that's the first one I tested with hydrochloric acid. I'm going to classify them as either acids or bases. Now the acids. Oh, I'm sorry. Do not write this down. We're going to look for a common theme here. You're not going to take these as notes. I'm just going to test a bunch of stuff. Now, I don't really like that red. I want a better red, but I can't really add. There's not much I can do.
Yeah, you can.
No, I
Just go
can't.
to the color thing.
I know, but the color, that's the brightest one I could find. I don't really like it.
Anyway.
Anyway. Well, I made red for acid because that's the color it turns litmus. And the first one I tested was HCl, and HCl is clearly an acid. All right. Now, here's another one that we know is an acid. This one says right on the bottle, sulfuric acid. All right, so I'll test him, and I know what's going to happen. I'll bet you. You know. If I put a little sulfuric acid in here, and I test it, I'm just going to put a blue one in because we already know what's going to happen. I'll put this blue one in, and of course it turns it red. So I've got sulfuric acid and hydrochloric acid right there. By the way, I'm going to line all these up here so you can see them. Okay, they can't on the camera, but that's okay. All right, sulfuric acid looks like that. I'm going to test something else that we know is an acid. Actually, I'm going to open it up right now. Soda is acidic, right? You guys probably know that. If I take some soda, I pour it in there, let's watch what happens. I take, again, another one of these strips. Remember, I'm looking for a common theme here. I dip one of these blue ones in here, and it comes out red. So this guy, by the way, soda has a couple of acids in it. Now, there's sulfuric acid, there's hydrochloric acid. Soda's got carbon dioxide in it. What kind of acid do you think that makes? Carbonic acid, very good. And it also, most sodas have phosphoric acid also added to it, usually to give it a little tartness and to make it a preservative. All right, so do we see a theme to all the acids, Michael?
Unique hydrogen bonds.
Yeah, it seems like they've got hydrogen in it somewhere. H, 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 H. Whether it's H1 or 2 or 3, they've all seem to have an H in them. All right, let's start testing some stuff that we know are bases. There's one in particular you've seen. I told you before when we used it in a lab on solutions, that it's used in Drano. Okay? And Drano has sodium hydroxide in it. Okay? Sodium hydroxide. Let me put some sodium hydroxide in here, some Drano in here. Yeah, Drano's nasty stuff. You don't want to get this in your eyes. If I put a red one in here, he comes out blue. Put that light for me just so you can see. Very blue. Yeah, he's very blue. All right, so yeah, it's about as blue as my shirt. Okay, so he comes out blue. I'm going to put him there, and I don't want to touch that, but there is my sodium hydroxide, and he looks like this. You can light off again so you can see it better. I know these. Notice I use blue for this one. I can see the blue better. You can see the blue better. It's just the red's not the greatest. Oops, I went too far.
There you went. Calcium hydroxide.
Okay, so sodium hydroxide is NaOH. Here's one we've used before too, lime water. This is stuff that we had bubble through. Remember the glass tube came out, bubbled it in there and turned to precipitate. Carbon dioxide turned it into a precipitate. Well, let's do some of him, see what he comes out to be. There's my Drano, by the way.
That's a better way to pour it.
Thank you. Okay, so there's my lime water. And I'm going to, again, test my strips in here and see what happens. I'll take a red one because I know what's going to happen. And I'll dip him in here, and he's going to come out blue. Doesn't look as blue as the other one, but he's blue. And really, there shouldn't be much of a difference between them. This does not tell you how dark blue it is. Doesn't really tell you how basic it is for litmus. It either turns red or it turns blue for the most part. All right? So we know lime water. Now, by the way, as I've said before, lime water is not made from limes, as in lemon and limes. Lime water is made from the kind of lime you would put on your baseball lines, for first base and third base line. Those lime, although now they use probably a paste of some type. Calcium hydroxide. And here's some antacid. Now, what would I expect an antacid to be? A base. All right. I'll open up this antacid. You guys probably don't use this because you don't have the indigestion that you guys give me. And I pour this in here. And when you get older, you use a lot more antacids, believe me. Sometimes you use uncle acids, but antacids are usually better. They're the female version of.
Females are clearly
Caitlin's still like, what? Antacids? Uncle acids?
I got it.
Now she's got it. Okay. All right. Let's test this guy. This one's hard to see. Why? Because he's also white. And so it's going to cover up. It's going to cover. Turn the light on for a second. The color here, but it's not. It is turning it blue. All right. It's just it's kind of hard to see past the white. I have to put him. I'm running out of the room here. This is the last one I'm going to fit on there. There are actually, if you look at the active ingredients on a bottle of liquid Tums or whatever this Malox or whatever, turn the light off. You'll see at least 2 active ingredients would be magnesium hydroxide and aluminum hydroxide. Oh wow, we have definitely found a pattern here, right?
Hydroxide.
Yeah. It's like all the bases have hydroxides, and all the acids seem to have H's. And that's a very good pattern. We have definitely found something out about acids and bases. However, we have some formulas where it's not so bloody obvious. Okay? For example, look at this guy, and that guy, and that guy. It's not going to be so obvious about these guys. If I were going to make a suggestion about each of these, that guy right there, probably going to say he's a what? Base. This guy right here doesn't have any OHs. It only has H's, although it's not in the right spot. Probably going to say he's an acid. And this guy, I got no idea what he's going to be, right? So let's test each of these. See if you can figure out which one this is. All right? This is vinegar. We know vinegar is going to come out to be an acid. One of those up there is vinegar. But you may be surprised to find out which one. Watch. All right? We know it's going to be an acid, I'm sorry. Yeah, and only something weird is going on here because I dip him in here, no surprise. He comes out red. Okay, you'd expect that. Turn the light on for a second. I'm working you over there, I know. And I'll put him over here, and there's my vinegar. But the problem is, light off. Problem is, this guy is vinegar, and he shows up over there. He's an acid, but he ends with an OH. Here's NH3. That happens to be something else you have around your house, ammonia. Take a little bit of ammonia. And again, he only has NH3. He doesn't have an OH. But when I put my red litmus paper in here, light on, it comes out blue. That's not good. All right, now that's my ammonia. And the last one, I know you could tell me what it is. I put some this morning from home. Brought some in. What do you think this is?
Orange juice.
Orange juice. What's it going to come out to be? An acid. And that's not a surprise. It will. But his formula, the way I have it written up there, would be very difficult for you to know. But he is an acid. Turn that light off. He shows up. Ammonia shows up over here, and the citric acid shows up over here. By the way, I purposely wrote these out. There's a lot of ways. Larger compounds, organic compounds like this one and this one, can be written out different ways. And because of that, I often have a hard time telling just by their formula whether they're an acid or a base. All right. But we do have some hints here. We definitely have some hints. Acids usually seem to have H's. Bases usually seem to have OHs. But we got a problem. That's not good enough because we got guys who we can't tell by just that. So what am I going to spend my time today doing? Really showing you the difference between an acid and a base. The actual definitions of acids and bases. Okay? So get your notes out. And I'm going to tell you how you really can tell. It's not enough to just basically look at the formula. Two definitions I want to give you. Now I'm going to have to move these bottles out of the way because you won't be able to see very well. I'll leave the smaller ones here. Now, there actually are three major definitions for acids and bases used by chemists. However, I'm only going to give you two. The third one is kind of more complicated. The first one's called the Arrhenius definition. It's the traditional definition of what makes something an acid. And it defines an acid based on what kind of ions it forms in solution. That's what Arrhenius says. And by the way, the reason you actually need three definitions, because some things are clearly acids, but don't fall under one or the other of the definitions. But they're definitely acids. Okay? And you'll see why as I go along. All right, Arrhenius acids, he says, Arrhenius says that an acid is anything that forms hydronium ions in solution. That's why I mentioned that word a minute ago. Notice what a hydronium ion is. Look at the formula for the hydronium ion. Something you've never seen before. H3O, not H2O. How do you think you get an H3O? What happens to get an H3O? What do you think? No idea. Well, he's very much like what? Water. Except he has an extra H, right? Where do you think he got that extra H? From the acid. From the acid. Yeah. Let me show you an equation, a very simple equation, one that you're going to use a lot in the future, and an acid that we've used a bunch of times in the past, HCl. If hydrogen chloride, which you guys all think is a liquid, it's not. What you're pouring out as hydrochloric acid is not actually HCl. It's a solution of HCl gas dissolved in water and reacting with water, actually. And what you get are hydronium ions and chloride ions. Now, those chloride ions, I don't care about. That doesn't make something acidic or basic. But I do care about, I do care about the hydronium ions. Do you see what happened here? You don't have to do this, but look what happens. this H from HCl breaks up and adds onto the water, right? So that makes him H3O instead of H2O. He took with him, he left behind his electron, and one proton, one hydrogen ion is a proton, is positively charged. Meanwhile, this guy, when he left behind the electrons. But let's just draw out for a second. Here's HCl way back to chapter probably 3 or 4, Matt. I know, there's stuff going on back there. Don't worry about it. Way back to chapter 3 or 4. Okay? That's what that guy looks like, right? If you were to draw an electron dot notation for him, the Lewis structure. When he leaves those electrons behind. Chlorine has an extra electron. He doesn't have one, so he's got a positive charge. He adds on there, hydronium ions have a positive charge. He leaves behind chloride, has a negative charge. And those are ions. Okay? So that makes HCl an acid. Because he formed these guys. This is the key. He formed those guys. I'm going to turn that off now. All right. Well, before I do that, I'll just give you a copy of the next thing. We're going to be using that for the next period. Actually, you only have a single today, right?
Yeah.
Your class will be using that, not you guys. A base, according to Arrhenius, makes hydroxide ions.
He forgot and we're all about black.
Okay. So he says an acid, and by the way, both of these things make sense to our formula. Look here. Remember our hint at the formula? Our hint that makes something an acid, well, a minute ago we had up here, all those acids pretty much had an H in them. That's nice, because any one of those H's, whether it was H2SO4 or H3PO4, they could give an H to water and make these hydronium ions. And all of our bases had what next to them? Yeah, NaOH or CaOH2. They all had OHs in them, and that's nice because that's what bases do. As a matter of fact, watch this. This is what happens when you put sodium hydroxide in water. I could have asked that on the test yesterday. Couldn't I have? If I said sodium hydroxide dissociating in water, would you not have written that? Isn't that what you all would have written on the back side of that test? Sure. Now, you didn't know at the time that that's what makes something a base, making these particular ions. So I'm looking for these guys or these guys, according to Arrhenius. If I've got hydronium ions, I've got an acid. If I've got hydroxide ions, I've got a base. Okay? Now that is nice, but here's a problem. Does anybody see a problem? Both of these acids and bases require what to be around in order to see if you have an acid or a base? What do you have to have besides the acid and base itself? Water. Because in this case, the acid reacts with water. In this case, although I don't always write it down, it's dissolving in water, right? So I have to have water around, or according to Arrhenius, I don't have an acid or a base. Well, that's not true. I absolutely can have an acid or a base even without water. And that's why we have a second definition. We have a definition called the Bronsted definition. It talks about what happens, how something can be an acid or a base without necessarily having water around. Watch. This is the Bronsted definition. By the way, you're going to get a worksheet where you're going to be asked to identify the different types of acids. That's either Arrhenius or Bronsted. So I hope you're paying really good attention here because you're going to get that worksheet by the end of the period. All right, Bronsted. Base. Here's what he says. Bronsted says, you know what? It isn't about water. It's just about what he's doing, how he's acting. Now, some of you guys act like an acid sometimes. What does it mean to act like an acid? Well, let's ask somebody who knows. Michael. That's just kidding. Now, what does it mean to act like an acid? It does not mean you're acting like Anthony or Marie. It means It means that you are donating a hydrogen ion. That's what he says an acid does. I say an acid does other things. But we'll see. See who's right. Now, an acid absolutely donates hydrogen ions. And you may remember from my previous example that that's exactly what hydrochloric acid was doing when he was forming the hydronium ions. Doesn't have to be, but it was doing that. You know what Bronsted says a base does? Accepts a hydrogen ion. He accepts an H from somebody. Now, there are times when these two definitions, the Bronsted and the Arrhenius definition, overlap. And you'll see that. I'm going to go back to the previous board in a minute and show you that. Matter of fact, before I give you my example, let me do that right now and show you how the Arrhenius and Bronsted definitions do overlap in some cases and don't in others. Look, back here. According to Arrhenius, we know HCl here is an acid because he forms these. And we know NaOH is a base because he forms these. But we also, according to Bronsted, know he's an acid. Because what did he do to make those? He donated, he gave away an H. He was HCl over here, now he's just Cl. He donated, and this guy accepted an H. According to Bronsted, then, HCl is an acid no matter what. He formed hydronium ions and he donated. According to Bronsted, is NaOH a base? Did he accept a hydrogen from anybody in this equation? No. So he would not qualify as a Bronsted base. But he does qualify. You know who does qualify as a Bronsted base, surprisingly enough, in the previous equation? Who?
Water.
Water. Water, according to Bronsted, in this equation, is a base. You said, well, I thought water was neutral. True. If I put a piece of litmus paper, red and blue, into water, it'll come back out neutral. But that doesn't mean water can't act like a base. All right? When he is accepting an H, he is acting as a base, even though he is not basic by himself. By himself, with no one else around him, he is neutral. But he can be an acid or he can be a base depending on what's around him. Now let's get back to my Bronsted example I want to do. Notice how my next example up here will only fit one of the definitions. Only the Bronsted definition. Take a look. Copy that down. By the way, this is exactly what you're going to be doing in a few minutes. Telling me whether they're Arrhenius or Bronsted, acids or bases. By the way, I did say I'm going to forget to say it again. There is a third definition, the Lewis definition, which I'm going to leave out. It has to do with electrons. All right, I'm going to leave that out. So sometimes you don't even have an H. You just have electrons being transferred, and that would make something an acid or a base. But we're only going to do Bronsted and Arrhenius. Okay, do you see why? In this case, what's going on, H is leaving HCl, right, and adding on to here. Do you see how that's happening? Everybody's looking here and seeing that obviously he was HCl over here, and now he's just Cl. He must have lost or donated an H. He was NH3 over here, now he's NH4 over here. He must have accepted an H. Knowing that, who is the acid and who is the base in this case? Well, look at the definition. An acid is anything that donates an H. Who's donating the H? HCl. So he is our acid. NH3, meanwhile, is accepting the H, forming an H4, and therefore he is our base, according to Bronsted. Well, let me ask you this. According to Arrhenius, are either of those guys acids or bases? No. According to Arrhenius, neither of these guys are an acid or base. There's no water around. There's no hydronium ions. There's no hydroxide ions. There you have it. All right, now, I'm going to do several examples because let me show you your worksheet, which won't take you very long to do. What are we over at 22, right? This isn't going to take you very long to do, but it's not as easy as you think. Let me do some examples. on the board here. Copy this down. Look at that equation. And I'm going to ask you, and by the way, every question when I ask it, I'm only looking in one direction. I'm only looking at the guys over here. Your answers are always going to be the guys over here, going from left to right, what's happening. So going from left to right, do I have, and by the way, I'm going to give you a little hint here. Always ask yourself about the Bronsted one first. Look at who's donating or accepting. What's going on here between here and there? What did the water do? Donate or accept an H? Everybody agree? Since he donated an H, that makes him a Bronsted acid. So you can put that little BA for short. You're going to do this on you can do this on the worksheet as well. He is a Bronsted acid. What happened in H3 from here to here? What do they do? So that makes him a Bronsted base. You see it? Now comes the second question. Do I also have an Arrhenius something? Yes. What does Arrhenius say? The main thing for Arrhenius, he says you've got to make what? Hydronium or hydroxide ions. Do I have hydronium? Which ones do I have? I have hydroxide ions. There they are. Now I know you want to do. You want to write down Arrhenius over here for the hydroxide. No. It's not the hydroxide that is the Arrhenius base. It's the guy that made it. So, who is it that made the hydroxide? No. A guy will not be, and I knew that would be your next problem. A person will not be an acid and a base in the same problem. Who is the Arrhenius base? Who is responsible for those hydroxide ions? This guy. The one who's also a Bronsted base. So whoever, that's why I said to do the Bronsted one first. I'm going to do several examples here, so don't worry if you didn't get that the first time. Always do the Bronsted first, because once you know who the base is, or the acid is, that's who the other guy will be. It'll always be the same. You're not going to have a guy who's an acid and a base in the same equation at the same time. So that's your final answer to this. NH3 is both a Bronsted base for accepting a hydrogen and an Arrhenius base for making hydroxide ions when added to water. Water is only a Bronsted acid by donating the H. Let's look at the next one and see if you get, we'll do this one together. Then I'm going to have you do some by yourself and see if you get them right. Let's look at this guy. Always do the Bronsted ones first. And Bronsted means who's accepting or who's donating. So, what is HF doing from left to right here? Donating or accepting an H? Donating. That makes him a Bronsted what? Acid. What is NH3 doing from left to right? He's accepting. Makes him a what? Bronsted base. Bronsted. Bronsted is the one who says about donating and accepting. Now you ask about Arrhenius. Do I have an Arrhenius anything here? No. That's my final answer. He's an Arrhenius, I'm sorry, he's a Bronsted acid, he's a Bronsted base, and that's it. Nobody's Arrhenius because I did not make hydronium or hydroxide atoms over here. Now let me have you guys, we'll go over them, but I want to have you try the next two on your own first. See if you really understand this. Try that one. See if you can figure it out. Try that on your own. Your answers underneath each of these should be either BB or BA or AB or AA. Let's see how well you did. I would look, like I told you, to look for the Bronsted first. Is HCl doing? What's he doing? He's losing an H. He's giving this H up to him. That makes him a Bronsted acid. What is water doing? He's accepting one. It's going from H2O to H3O. That makes him a Bronsted base. Did you all have that much? Good. Do I also have an Arrhenius something? Yep, because I've got that. Now, the biggest mistake I will see is who's the Arrhenius something? It is HClO3. He is the Arrhenius acid. Why? Because he's the guy responsible for making those hydronium ions, and you can't have the same guy be an acid and a base. In other words, if you're going to put him over here and say, oh, he's the Arrhenius one. Water's never the answer for Arrhenius, guys. For Arrhenius, water's not the answer because remember, Arrhenius says you got to add it to water and see if it forms hydronium hydroxide ions. So water's not the answer for an acid or a base. It's the guy you're adding to water who is either an acid or a base. One more. Last one, then I'm going to pass out your worksheets. Matter of fact, while you're doing that, so we make sure you have enough time, I'll pass them out while you're doing it. Now I'll go over it. You're not really an acid. Always do the Bronsted one first. Do we have a Bronsted anything here? No. I don't have anybody losing or gaining H's. No one's donating one H to another compound like I had here and here and here. So what do I only have here? What is AlOH3 in this case? An Arrhenius base because he formed hydroxide ions. Exactly. So there you have it. All right. You have the worksheet. You know